If I had a professor that, I have one professor, I was taking Chem 2 at Louisiana College, and she said the highest grade on the final became your grade in class.
Like for whoever scored the highest on the interesting.
I stole it, but
I scored the highest. I scored the highest.
you scored the highest?
Yeah.
All right. Well, hello everybody. I have a feedback. You can give me some feedback on the exams, like a Kahoot thing for that. We'll do that in a little bit in case anybody filters in a little late. So I have not graded the exams yet. I have not begun grading the exams yet. Based on kind of working through it during class, I think and hope it was a challenge but reasonable. That's usually my aim. So we'll see what you felt about it. And then, of course, once you get the grades back and see what you got credit for and all that, maybe your opinion will change again. But this way I'll get your raw opinion, still fresh on your minds and everything. But before we get to that, I'm going to start us off talking about granular filtration and really kind of come back to what we started before the exam. So here, what we're going to do today is take a look at these granular filtration systems, which are, like we talked about last week, they are essentially using sand grains or some similar media to capture particles. And you remember watching the backwashing of these sand beds and all this nasty particles coming back out. So all those had been collected over the course of many hours of filtration, and then they're backwashed into a wastewater stream. So essentially what we want to do in terms of math is figure out a robust way to describe how often we need to backwash and how to account for that amount of water so that we know how many filters we need, for example, in a plant, given how quickly we can add water to them and given their dimensions and all that. So basically we just need some math that shows us how to deal with filters that have to come offline and have to waste some of the water we produced when we do so. So that's the issue here. And so kind of the most important parameter then is, well, how long do we actually filter? So what does that cycle time look like? If we have a total cycle that includes a rinsing phase, operation phase where we're producing, and then we stop to backwash, all of that comprises one full cycle. How do we determine when to stop the cycle, right? So how do we determine when to stop filtration itself? So there's really three methods we can use. One would be head loss. So that's pressure. We often call it hydraulic head if we're talking about water in a pipe or in some hydraulic system where we have some height of that water pushing downwards, giving us a pressure. So that would be head loss, meaning over time through the filter, we're getting a loss of pressure that's increasing over time. So our head loss is increasing, meaning that there's a bigger pressure drop there, pushing water through the filter. Which also typically means that essentially what we're going to do is just add more water on top at a certain flow rate in order for it to be pushing water through. It's just going to stack up a little higher and higher over time, automatically kind of calibrating for us that pressure. Another way to do it would just simply be to add a time limit. If operators know that, based on their experience, this thing is good until 36 hours. Maybe they'll set a time limit of 36 hours. They're always going to stop and backwash. Usually they'll also be monitoring the head loss in that case, and hopefully always the turbidity, because that's the particles that we see come through the water. If we start seeing particles escape, then we have an issue, right? So we have contaminated water coming through. So at some level, we reach a point where we say, okay, well, we don't want any more operation given the turbidity. So that's the first one we'll take a look at to demonstrate kind of how it would look in practice. What would the turbidity look like, and how would we go about setting a limit in that manner? So if we have a system here and we start with a freshly cleaned or freshly installed filter, we can say this is clean to begin with. Then the first little bit of time is going to be that rinse stage, right? So we say we'll rinse there. Then we're doing production for some extended amount of time, hopefully. So we'll have production or filtration time. Then we're going to stop and have a backwash. Now this might include an air purge as we saw. So I'll just add a little notch there. So air purge, which is really kind of tied to the backwash itself. But of course, we're not using any water during that time. So it's just sort of time that the filter's not doing anything. We're not consuming water during that moment. We're also not producing water. So then we'll have our backwash here at the end. So what does turbidity do then over the course of this period? And how does that relate to some limit we might place? Let's imagine we place a limit to say, well, if it's any dirtier than this amount of turbidity, then we're worried about safety and the effectiveness of our disinfection step next. So anything above that turbidity limit we're gonna say we should not operate. Okay, so that's gonna be our somewhat arbitrary, maybe there's some rules in place, turbidity limit. So with a clean membrane, or not membrane, clean filter we talked about last time, essentially what's gonna happen when we first start pouring water through it is we're gonna have some debris come out. So whether it's because we just backwashed it and there's some particles still stuck in there and ready to just come out as soon as we push water through and it starts kind of letting the particles, the sand grains settle into place again, or maybe it's a brand new filter and we just have specks of carbon or whatever is coming out, right? Like we put in a new Brita filter, we want to pour a couple gallons of water through it, get all the little black specks you don't want to drink. Probably be okay, but you just don't want to because it looks gross, right? It's that process, right? We're going to rinse it and provide some amount of time, usually about 15, 20 minutes of operation. And the turbidity during that time is probably going to look something like this. It's going to spike up a little bit and then start coming back down. And by the time we start operation, we'll start operation with a pretty low amount of turbidity. And it may actually improve for a little while particles start collecting in the filters. It causes more particles to be removed by the filters. So it's like an enhancement effect for a little while. So we could even draw this as for the first maybe 10 hours or so, decreased a little bit, and then eventually we're hitting that spot and we're saying, oh, we reached our limit, and so we're no longer going to produce any more water because we are at our turbidity limit. So that would be our scenario where we're only going by turbidity. We know we have this rinse time period, and we expect the particles to be too much during that period, quickly dropping off. And then during operation, we continue until we hit that limit and say, okay, that's the time limit. So that's kind of one way. That's probably the safety first type of option, but that doesn't give you a whole lot of control in terms of routine maintenance, routine design. You'd like it better to actually scale it back a little bit, probably to say this is in place in case something goes bad. But really, we probably want just a generic time frame or pressure head loss to kind of give us what's going on. All right, so in terms of producing water, we really are looking for the net amount produced. So we've got a couple of equations to look at, but real quick, first, a typical production rate in terms of how quickly we're loading water onto our bed. So if we have a sand bed here, we're loading water onto it at some rate, and we're going to describe that loading rate as essentially a flux, because it's going to be some amount of water going through some area. This is going to be something like liters per square meter per hour. or something, right? Or it could be, or I guess seconds in this case, right? You could also say that's cubic meters per square meter per second, which could also be meters per second, right? So you could look at it just as the velocity of water going through this plane, okay? And that's all just sort of how the units can work out. And just a couple examples here. A typical production rate for these types of filters can be anywhere between 5 to 25 liters per square meter per second. Okay, so that would be then 0.005 cubic meters per square meter per second. So several of these bottles through 1 square meter of filter area every second, maybe up to 20. So pretty good flow rate. That's 2 to 10 gallons per minute per square foot, if you wanted to go that way. And this loading rate is what we're going to call a production rate or loading rate. Those are kind of interchangeable terms, and we're going to describe that, according to the book, as lowercase v subscript a. So the rate at which we're loading, it's kind of like a velocity here onto that area. So lowercase va, we can describe that as, just looking at the flux term, that's going to be the flow rate per filter area, right? Which can be described, so that's flow rate per filter area. And we can kind of elaborate on that and say, okay, well, that's the volume of water going through per time divided by the area. And so with this, we can rearrange if we wanted to and say, well, to solve for the volume, which is something we'll be doing a lot, we're going to have the volume equal to then the loading rate times our area of the filter times time. And we're probably going to need that, or I guarantee you will need that for each of the different categories, for how much volume we produce during filtration. You'll have that loading rate, you'll have the area of the filter, and you'll have the time spent doing filtration. And then you'll need the amount you used for rinsing. You'll need the volume for rinsing, and you'll find that by that loading rate, because during rinsing we'd use the same exact loading rate as normal, times the area of the filter, and then the time spent doing the rinse. Okay, so a lot of this is just going to be breaking it down in terms of like how much time did we spend doing each part. Okay, so one note here is when we talk about these flow rates, what I'm describing here as Q and area of the filter, I'm saying that for this specific loading rate, I'm saying that's the flow rate for this particular filter, going through this filter. That's not the flow rate that the plant has to meet. We'll come back to that concept because that has to be, we have to account for downtime of the filters. So what I'm describing here in relation to this loading rate is the flow through the filter while producing water or while backwashing, whichever volume we need, right? So this one is for while performing, and I'm just going to give it a little label, operation X. If I put a little X down here. Okay, so that's, I just want to clarify that because you'll have in many of the problems, like a plant has to meet, 10 billion gallons per day of water or whatever. And we're trying to do that with these filters of some size. How many filters do we need? Each of those filters, we can describe a flow rate for that particular filter during operation, and that's separate. So keep that separate in your mind from that total that we need to make from the plant. Does that make sense? All right. So let's talk about kind of typical, the typical scheme of a given cycle and how that impacts how efficient the filter is on a water basis, and then we'll get on to the effective loading rate where we average the water produced over time. So a given cycle, I'm just going to write this up first, is going to be, we have that rinse time, right? This is going to be rinse or ripening. That's typically about 15, 20 minutes. I'll just say 15 minutes, okay? Then we have the production. And that's going to be anywhere from, 24 to 100 hours. Okay, and obviously we want that to be a large number compared to how much time we're spending rinsing or backwashing. Wouldn't make much sense if we had to use all that water we produced. If we only could produce for an hour, we'd use half of it for rinsing and backwashing. So then we'd have an air purge. We even saw in that video that probably only takes about 5 minutes to push a bit of air through and then prime the pumps again and get it back ready for water. And then our backwash, again, typically takes something like 15 minutes. Okay, so overall about half an hour or so per cycle is spent offline not filtering water. So then in terms of the efficiency of the water, we have this equation here where we have nu as our little parameter equal to the amount of volume produced during filtration minus the volume wasted for backwashing and the volume that we couldn't use for the rinsing. Okay, so that's all that divided by the total volume filtered. This will give us our filter efficiency, meaning what percent of the water that we are giving to this filter is actually coming out as usable clean water, right? So it's a water efficiency basis. And if you look at this equation, you'll see that that'll give us a fraction. And assuming that VR, so the rinsing water and the backwashing water, are much smaller than the amount we filter, which should be the case if we're going tens of hours versus half an hour, that should be that fraction should be a pretty large fraction. So it should be close to 1, right? Should be in the 90s, hopefully, right? So something like 95% or better, often. So we'll just say 90 plus is typical. Okay, so then we need the volumes for each of these, and that's what I was just talking about a moment ago. We take that equation where we were talking about this in terms of kind of a flux, where we said, we started by saying, okay, this loading rate, VA, some loading rate is going to be equal to the flow rate through some area given some amount of time. We solve that instead of using the flow rate. We could put that into volume. I'm sorry, that would be time's already accounted for there. We could rewrite this as volume per time with the area as well. And so with that equation, we come over to these. And here we have the volume filtered. It's the area of the filter times that loading rate times the time of filtration. Then the rinsing is going to be the area times the loading rate times the time spent rinsing. And then finally the backwash, we're going to have a different loading rate here, VB, possibly, in case we are backwashing at a faster rate than we put water forward onto it, which is certainly possible. Our only limitation really is we don't want to push all the sand grains out with the particles. And so it's pretty common to have a faster backwashing step than the loading rate. But I guess a default would be to treat it the same if you were not given any information about it otherwise. So VB here is somewhere between 1 to 2 times VA. Okay, this is that's typically the case. And we can assume VB equals VA if no other info is given. and you have no way to solve for it. Okay? And that's simply a fairly practical matter. You know, if you can backwash it faster, your pumps are set up where you can do that. You might as well get the particles out of there a little quicker and be a little more disruptive to the media so that it has just that extra capability when you clean it. You'll lose a little bit more water, but hopefully you can do the process quicker, right? So it's kind of the same deal. If you had to spend more time, but you lost less water because you're not pumping it as fast, well, that's also time you're not spending filtering. So it really all kind of boils down to whatever just makes sense for the system. Okay, so that's our filter efficiency, and we just have to calculate the volumes for each of those portions, and it's pretty straightforward. You just have to make sure you're thinking in terms of the cycle time, right? So it may make sense to draw this up, or just make sure that you have a good understanding of what components play into the cycle time. Once you have that, kind of everything else can fall into place nicely. So the net loading rate then, we're going to use, the book has lowercase r subscript EF, so the effective rate at which the water is loading. So RF, or EF, is always going to be less than the loading rate we apply to the filter, but hopefully not by too much, right? So effectively, it's going to be, because this is accounting for the time we're spent not filtering, it must be lower than VA, because VA is simply that loading rate during production of water, and we're not producing water the whole time. So it's going to be less than, but hopefully but not by too much. And in fact, if we think about it, REF will be close to, but not equal to, the loading rate times that water efficiency. But this is not exact, right? So this might be a good way to check yourself. Don't use this as a calculation tool, but it may be worth double checking to see if your answer is close. The reason it's not going to be exact is because this net loading rate accounts for the time where we rinse, time we use for air purge, which the water efficiency has no clue about. That equation doesn't manage that at all. So if we happen to have like 10 hours of downtime for maintenance that's neither consuming or producing water, that's not going to get caught in our filter efficiency water equation, but it certainly would drag down our effective loading rate, right? Likewise, if we spent, for some reason, a lot of time air purging or something, the same case. So it's not going to be exact, but in most routine operation, it's going to be pretty similar. So I just kind of a little frame of reference there. Okay, so the formula for this then is essentially going to be the amount of volume that effectively we get over a cycle time, right? So that's going to be I guess one way to write it would be to say the volume produced during filtration divided by the area minus the volume used during backwash over the area minus the volume rinsed over the area, all that divided by the total time, the time filtered, so that would be TF here, minus time backwashed, that'd be here, minus or plus the time rinsed, TR, and plus the time spent air purging. All of that together, of course, is the total cycle time, which we could just say time for the cycle. And so we can simplify that equation by saying that's going to be the volume over the area times time, right? That was our equation a few minutes ago, was saying loading rate is going to be that volume over time per area, right? And so in this case, that's exactly what this is, but what we're doing is we're also subtracting the amount of volume we wasted during backwashing and rinsing. And so in this case, it's that instead of VA, we have the effective loading rate, so REF, is that kind of that effective volume. We'll just say volume effective over area of the filter times the total cycle time, right? And that's why if we extended this air purge time or something, or had some other interruption, that really could change the effective loading rate. Okay, but if the air purge is 5 minutes, the difference between the effective loading rate and that actual filtration loading rate times this nu is going to become pretty small, right? That they're going to be pretty close. So it's probably never going to be equal unless we have a very simple case, but usually it will be pretty close. All right, does that make sense? The issues? All right, so overall it's pretty straightforward. It's really a matter of recognizing what you need for understanding the full cycle. So we've got a problem. Before we jump into that though, what I'll have you do is give me some feedback about how you felt on the exam. All right, so fire up the Kahoot, go to kahoot.it, and we'll have and then it'll ask you for a pin, so you put in that number there. And use your 8, 9 numbers. Please. Unless you don't want credit, of course. And by the way, I'm never going to bother to go back through these and look at like, okay, who said exactly what and how did you feel about the exam or whatever. So feel free to be honest. I mean, if you really just want to answer randomly, I guess you can, and I won't know that either. But it'll help me with the design of exams and all that, and to get a good feeling of how you feel about it if you answer honestly.
So I won't be reporting to the dean.
No, I mean, I don't think I put any. If I put any options that would be report worthy, that would be my fault, right? And then I'd be like. No, go to kahoot.it, not .com. If it's asking for an account, it's probably taking you to kahoot.com. Using an app, gosh, it's intense. All right, anybody else need some more time? Issues? All right. Okay, so how did you feel about the length of the exam? All right, so a lot of just right. Nobody said it was short. A couple people said it was too long, but most was either long but manageable or just right. So that's pretty good. And you know, of course, I don't want it to be too long, but you know, if there was a couple people that really got stuck on something, that's unfortunately typical. So how do you feel about the preparation for your preparation for the exam, kind of on your end? There's an option for that.
I'm not sure.
Okay, so unfortunately, a lot of you don't feel like your preparation helped much. some of you felt prepared, some of you are not quite sure, gonna see the grades first, and then of course some of you wished you had prepared better, understandably. Okay. What did you think about the difficulty of the questions? I know how that goes.
Dynamics right there.
Okay, good. There's not too many of you who are like kicking yourself right out of the doorway, right? Okay, and all right. So one of you is feeling really good about it, or maybe pressed the wrong button. So unfortunately, nobody actually felt like it was mostly easy. It's always nice if somebody does. Okay, so how comfortable are you with the mass balance reactor type kind of problems, or that aspect of the problems? Okay.
I accidentally clicked that.
The green?
I clicked blue.
Oh, blue.
know.
Which you click green, or which one did you actually click?
I put green
Okay.
on accident.
Well, that's good. I mean, I'm glad that I'm glad that nobody feels like they have no idea about it. So that's a good thing. All right. Good. How about the chemistry?
Are we talking balance,
Well,
or are we talking about concentration?
It's kind of the stuff that we did. Oh, I didn't give you very much time on that one. Sorry. I need to fix that. All right. So I don't know why that gave you like 10 seconds. Okay, but if this is to be trusted, a bit confused, some mostly knew what you were doing. Okay, and we'll get a little bit more chemistry review, I guess, in the next section when we kind of cover the equilibrium stuff a little more for the chlorination. The one in the exam was just an ionic strength problem. It did require you to do molar conversions kind of stuff, so it hopefully was will give you some reason to focus on that if you need to. Okay. How about the sedimentation problem? Again, I'm sorry, didn't mean to leave this so short.
Is that the one with the two tanks? You like find the area of the two tanks.
Yeah,
The two
yeah.
storage areas.
I forgot the formula for the tanks. So I just did pile
Oh
four,
no!
I know.
Height times the radius squared, and do radius times 2.
Well, I mean, the area of a circle is pi r squared, right?
Yeah, and then we just add the height to it because it's a cylinder.
Yeah.
You may have done that right.
Oh, okay.
We'll
May
see.
have accidentally done it. Like a
Second guessing yourself. Because I think I gave you a radius, not a diameter that time. Because a lot of times we've just been working with diameters, as said, but I tricked you by making it simpler, right? So then you're doubting. You gotta look out for that. It's sometimes tricky when I go simpler. Okay, so most of you felt a little better about that. Good. All right, last one. How about the coagulation flocculation problems? How'd you feel?
Which one was that?
Jar tests, I think. Right?
No, I didn't change my answer.
Verbally, did you guys feel bad about it? Or?
I thought it was the runoff problem, but
The runoff problem, I think, was also sedimentation. So there was that one and that multiple pond.
How is that possible?
I'm yellow.
Okay.
I'm not
Okay. All right. Okay, sounds good. Thank you, guys. Sorry about the short time frame there. All right. So overall, it seems like still a bit of hesitation. Not quite sure how you feel about it in a lot of cases, or but at least not too many people were feeling like, oh no, this is the worst thing ever. And if that is you, talk to me. Happy to try to help you. A lot of times it'll just be a simple concept that's like you just missed that one little piece or something, or looking at it the wrong way. And if we can clear that up for you, helps the rest of the semester. Very happy to do that. Okay, so coming back to the granular filtration then, we have this problem we can work through. So I'll read it through with you. We'll kind of draw it up, and then I'll give you some time to think about it and see if you can tackle this given what we've learned so far. And I'll write up the equations that we just saw as well. Okay, so we have a conventional water treatment plant that treats 2.4 cubic meters per second of river water. Filters in the plant are 8 by 8 meters in terms of the surface area, and they operate on the following schedule. A filter is cleaned once in each 24-hour period, and the backwashing rate is 10 liters per square meter per second for a period of 8 minutes. It takes an additional 8 minutes to drain the filters and break up the media with air injection. Of the total filter cycle time of 24 hours, 15 minutes is used for rinsing the filter after backwashing. During production, water is applied to the filter at a rate of 5.5 liters per square meter per second. So part A is asking what is the filter efficiency, and then to follow that up, part B says what is the minimum number of filters required by the plant. Okay, so just a couple things here. They gave us a Q total for the entire plant here. The next thing they gave us the area of the filter is 8 by 8. So we can do a little multiplication, say that's 64 square meters. We were given a schedule of sorts. It says a filter is cleaned once in each 24-hour period. So that 24-hour period then should be the total cycle time. We were given a backwashing rate, so that means we have a VB that's not the same as VA. That was 10 liters per square meter per second. And we notice that's almost twice the loading rate here that was given right there. We're also given the amount of time for the air injection step. That was 8 minutes. We have a time for the rinse, which was 15 minutes, and a time for the backwash, which was 8 minutes. Okay, so we have a lot of times here, good amount of information there. And then the filter efficiency equation was just simply the volume, the volume filtered minus the volume backwashed minus the volume rinsed divided by the volume filtered. Okay, whereas the effective loading rate that we'll need in the next part, that is, again, volume filtered minus other volumes used divided by the area times total cycle time. Okay, so take a few minutes and see if you can get a good approach to that.
Yeah. Right. Everyone just needs the time that is spent. We're trying to do that, yeah. We'll get to the lines. The total filter cycle time, but we're not doing that. We're doing total minus the minutes that are used. We need time filtered, right? So would that be, yeah, would that be the total time minus the minutes of everything else? Wait a second. So yeah, it's time filtered. Right, what I'm saying with this assignment, because we know what everything else is, we go 12 times 24 hours. You know, we've got 8 minutes of one, 8 minutes of another, and 15 minutes of another one. So what would just be doing 12 minus those for a second? Yeah, that's what we have, TC. Yeah. 24 times 3600 minus 8 by 60 minus 8 by 60 minus 15 by 60. It's very real that it's that type of. 24 by 36 minus 60 by 60. All in brackets because that sum total is 2 multiplied by it. I got different one here. So, that's what I got for it. For T. Yeah. Oh, TM. Oh, okay. I'm sorry.
24.
No, I just clumped it together. I'm sorry. Yeah, we're gonna say one that. Do we need TF for anything else? AF would be TF. So far. That's it. Participants is 15 minutes. That still feels wrong. I guess it's like a backwash. That would feel some kind of makes sense. Read efficiency. Efficiency first, right?
Oh.
We're doing part of it. Well, yeah, if everything else is in seconds, then yeah, that'd do it in seconds. What I do? Well, you do it about a big, yeah. Yeah, was the big. But I mean, you're in the ballpark, it's off by 5%.
so let's go through this. Any questions up front? How do you feel about it? Felt all right? All right. So essentially this equation for the volumes here, I didn't bother repeating for you because this is the type of the equation I'm not going to put on your exam because should be intuitive, right? You should be able to get this given some information about how a flux works, right? So some flow right through an area. My expectation, and by the way, how did you feel about the formulas I gave on the exam? Was that good, helpful? Do you feel like what was not on there was something that made sense that you could kind of learn and apply for the most part?
I'd say like add, like if you're doing like area or something, I would add that.
Okay. So I think you had it right, and I as an engineer, I think I would expect you guys to know the area of a circle. Not to poke fun at you by any means.
Yeah.
I get that, but like that's probably something that you should all like. But that's true though for like let's say the volume of a sphere. Maybe I ought to give that because we went over it, but that's not as intuitive if you like forget. So I like that suggestion. So thank you. Not meaning to bug you, but overall felt pretty good about like okay, there's the technical thing. It's going to be there, and so yeah. So that's my aim, and I'm hopeful that this will fit in line with that. If you understand the concept of a flux, you should be able to get these volume equations here, given the situation. Okay, so for the problem, we really need to just get these 3 different volumes for part A, and honestly for part B as well. It's mostly that, and then apply it again with the kind of concept of a flux. So for part A, then we need these volumes, and we're given pretty much all the information except the time for filtration. Right, so we were given the cycle time, we were given all these times, and one thing that you might want to do, if not draw it up like the cycle scheme, at least write it up, right? So you have the time for the cycle was 24 hours, the time for rinse was 15 minutes, time for the backwashing was 8 minutes, time for the air purge was also 8 minutes. So that leaves us with a question about, well, what is the time filtration? And that's going to be the 24 hours minus the other pieces, right? Because that's the only thing left. So we can solve for that once we get that time for the filtration. Then we can solve for each of these and get our answers. I'm just going to go ahead and pull up Excel because that was kind of where I put all this. So if we take a look at it, sure. Okay. Okay, so if we look at it up at the top here, that's kind of what I wrote as. So we have the cycle time, 24 hours. I went ahead and converted that all to seconds, just because I thought that was going to be more convenient. Forgot. And so I went ahead and said, all right, well, 24 hours times 3,600 seconds per hour, 86,400 seconds. Time of filtration was unknown. Time of rinse was 15 minutes. Other two are 8 minutes. Went ahead, got those into seconds, and then I just subtracted. So if we were to select that cell, we can see what I did. It was equal to the total cycle time minus the other components, right? So it's pretty straightforward. We get our answers there. Then we can put it into the volume equations, and I just actually wrote this in. We could calculate the same thing, right? We could say this is going to be equal to the VA. If I had written it, I'm just going to write it in then. This was 5.5 liters. I'm going to go ahead and convert it to cubic meters, say 0.0055 cubic meters. So yeah, make sure everything's in the same units here. Cubic meters per second times the area of the filter, 64 square meters, times the amount of time filtered there. And we see that that answer should be pretty much the same as what I had written down. A little bit of a rounding error there, I guess, from when I wrote it in from previous notes or whatever, but it's basically the same. So we can do the same thing for the volume rinsed. We take the amount of time rinsed times that loading rate, 0.0055, times the area of the filter, which is 64 square meters. And same for the backwash. Got that time backwashed times this. This loading rate for the backwash was 10 liters per square meter per second, so that's 0.01 cubic meters. Again, times that 64. And so we get those three values, and then we can calculate our efficiency here based on our efficiency equation, right? So, and in this case, I'll update the accuracy a little and say, instead of B10, we'll use D here. Even a little more precise, so 0.979 or 97.9%, which is in line with what we talked about, right? It should be not quite 100% efficient, obviously less than 100% efficient, but not too far off given that we produce a lot of water. So that's part A. Then part B asks us what is the minimum number of filters required by the plant. And so here's where we would use some sort of a Q total and say, just based on kind of almost say common sense, we know that that's going to be equal to the effective loading rate times the area we have to filter. But this is not, so if we write the area we have to filter, that might be a little misleading. So I'll leave that AF as one filter multiplied by the number of filters. Okay, so that's probably the best way to think about it, is we have an effective loading rate. So we've already averaged for the downtime. So that effective loading rate times the area at which it's being loaded, right? Which is going to be the area of one filter times the number of filters we have. So again, this is a flux concept. We could take the flux here, the REF, say if the flux is equal to the flow rate per area, that's the same equation just rearranged, right? So if you get stuck on manipulating any part of these, think flux. We're going to deal more in depth with flux for the membrane filtration next time anyway. So the flux concept is going to be very helpful. Okay, so then we can solve this one and say, we'll solve it for filters and say the number of filters is going to be equal to the Q total divided by the R effective times the area of one filter. And so that's what I have right here, shown right there. So then when we solve that, we can say R effective then is going to be equal to these volumes that we calculated divided by the area and divided by that total cycle time, which I now have written here, so I can go ahead and just use the total cycle time. Just for the sake of accuracy, I'm going to say these are all D. Use those new ones that we put in just a minute ago. Oops, killed it. There we go. Okay, so that turns out that we have, when we solve that, well, first of all, our effective loading rate was 0.0052, whereas so VA was 0.0055 cubic meters per square meter per second. And we see if we calculate the REF, which we needed to do for this problem to solve for that, that came out to be 0.05526. We'll say 527 cubic meters per square meter per second, right? So what we see is the R effective is less than our loading rate. That should be the case. So if it wasn't, we knew we did something wrong. And that gives us, once we put in the numbers, a number of filters equal to 7.12. Now we're not going to install 0.12 of a filter. That wouldn't make sense. unless maybe there were like smaller compartments or something that you could just add. But realistically, you'd want a little extra breathing room for your operation anyway, in case you did have to do some unexpected maintenance. So in practice, you're probably going to set some sort of a design, a built-in error margin by design. And so perhaps even more than this, but at least by rounding up to the next number of filters, that lets us fully treat the amount of water that we need, because we can't treat it with just 7 filters. So we cannot round this down. And then that extra space there gives us actually capacity to increase our amount of production if we had to, or at least have more built-in downtime available, right? So that's kind of the situation there. And like I said, most facilities will design it with it in mind that sometimes you might have to clean out an entire filter or something. It's very rare to replace the media, but maybe they expect to every 20 or 30 years or something. Okay, does that make sense? All right. So I'm gonna, for the sake of the slides here, I probably ought to say Q total. We can relate that to the R effective times the area of a filter times the number of filters. Okay, and then we solve for number of filters. Okay, and I just had some more space to do that. Okay, so next time we'll look into membrane filtration, and at some point during the next unit before the second exam, we will have a little quiz. I might even just do it on a Moodle quiz, because I think I already have one built there on this assigned reading. So I keep mentioning it every now and then, but it will be coming up. It is relevant to, especially relevant to granular filtration, but there's a lot that went on, and granular filtration was one of the areas where they had a big issue. So definitely see that under the assignments in Moodle, and we'll see you guys next week.